Welcome to The Explainer. Today, we're diving straight into the invisible magic of amplitude modulation and looking at how it evolved over decades to power modern drone technology. We completely rely on these invisible waves to control machines in the sky, and understanding exactly how that works is honestly one of the most fascinating journeys in communications engineering. Here's our flight path for today. First, understanding amplitude modulation. Then, the math behind the signal. Next, decoding the message. After that, driving early RC drones. And finally, we'll wrap up with the modern QAM revolution.
All right, let's kick things off with Section 1, Understanding Amplitude Modulation. Okay, so to really get AM, we can't just look at equations on a chalkboard. Think of it as this incredible technological feat, literally attaching complex data to an invisible traveling wave. To wrap our heads around it, we've got to mentally separate the two signals at play here. First up, the carrier signal. This is our high-frequency workhorse, right? The delivery vehicle, zipping through the air. Then we have the modulating signal. This is the payload, the actual information we want to send. AM simply takes the amplitude or the strength of that carrier wave and varies it to match the message signal, all while keeping the frequency perfectly locked in.
Moving right along to Section 2, the math behind the signal. Now, let's take a quick look under the hood at the math. There's a vital concept here called the modulation index, or the Greek letter mu. It's basically just a ratio, the message signal's amplitude divided by the carrier signal's amplitude. It tells us our depth of modulation, basically how aggressively we're altering that carrier wave to fit our data. And here's the crucial part. You absolutely must keep this value at 1 or below. If mu creeps over 1, bam, you get overmodulation, which means severe signal distortion and lost data. Nobody wants that. So looking at this in the time domain, check out this really cool visual envelope effect. You see all those tightly packed high-frequency oscillations? That's our carrier wave doing its thing. But look at the outer edge. It expands and contracts perfectly symmetrically around the zero axis to trace the exact shape of our original message. That outline right there, that's the envelope, and it's the absolute key to how AM actually works.
Now, if we shift our perspective over to the frequency spectrum, we see the real cost of doing business with AM. The modulation process actually spawns two distinct sidebands, an upper and a lower sideband, sitting symmetrically on either side of the carrier frequency. Because of this extra baggage, AM requires exactly twice the bandwidth of the highest frequency in your original message. That spectral footprint is a massive deal. It's exactly why you can't pack radio stations or drone control channels too closely together without them bleeding into each other. Let's put some numbers to this to see how modulation impacts real-world radiated power. Picture an unmodulated AM transmitter pumping out a carrier power of 9 kilowatts. But when we modulate it, that total radiated power spikes to 10.125 kilowatts. So what's our modulation depth? It's a super simple three-step process. First, we just plug our known values into the total power equation. Next, divide both sides by that 9 kilowatt carrier. Finally, a little quick algebra to solve for mu squared gets us 0.25. And just like that, we've found our 50% modulation index. Pretty easy, right?
All right, on to Section 3, decoding the message. Okay, so we've beamed our math-heavy signal out into the ether. But here's the million-dollar question. How do we actually extract that data on the receiving end? The answer is beautifully simple, the envelope detector. This is a totally passive circuit. First, a diode steps in to rectify the incoming signal, which basically just chops off the entire negative half of the waveform. Then, an RC filter, just a basic resistor and capacitor, takes over. The capacitor charges up on the peaks of those carrier pulses and discharges slowly, tracing that outer envelope we talked about earlier. Literally just two simple components and boom, we perfectly recover our original message.
Which brings us to Section 4, driving early RC drones.
You know, the absolute genius simplicity of that little demodulator circuit is exactly why AM became the absolute backbone of early unmanned aerial vehicles. Long before we had complex digital links and onboard computers, early drone pioneers relied on AM because the parts were just unbelievably cheap and lightweight. The pilot's control sticks would mechanically encode position data into something called pulse position modulation, or PPM. Then, that PPM signal was used to directly amplitude modulate the radio carrier wave. Simple but highly effective.
Take a look at this vintage 1970s radio. Back in the day, this was absolute state-of-the-art. But there was a massive and frankly dangerous catch to this analog AM setup. Amplitude modulation is, by definition, super sensitive to atmospheric noise and electrical interference. I mean, even the electrical noise from the drone's very own motors could mess with the amplitude. This caused terrifying moments known as glitching, where the servos would randomly jerk around. Best case, it's scary. Worst case, a complete loss of control and a shattered RC plane. And that perfectly sets up Section 5, the modern QAM revolution.
So, to eliminate those awful glitches and, handle the massive data rates of modern sensors, engineers had to completely rethink the tech. Just look at this contrast. That vintage analog 70s hardware sitting right next to a modern digital gray-coded bitmap. It perfectly shows the leap we had to make. To crush the limitations of standard AM, the whole industry pivoted to quadrature amplitude modulation, or QAM. QAM is, honestly, a stroke of engineering genius. It fundamentally smashes amplitude modulation and phase modulation together. Instead of relying on a single carrier wave, QAM uses two, a sine wave and a cosine wave. They operate on the exact same frequency simultaneously, but they are completely out of phase with one another. By tweaking the amplitude of both carriers at the exact same time, QAM lets us pack way more bits into every single symbol. We're talking a massive upgrade from simple analog pulses to dense digital constellations like 16 QAM or 64 QAM. It is incredibly efficient. And that leap in efficiency, that's what changed the entire game. Standard AM could literally never handle a video feed, but QAM completely solves that low data rate bottleneck. This digital magic is exactly what powers the cutting-edge systems dominating our skies right now. It's why tech like DJI's OcuSync or even standard modern drone Wi-Fi can stream crystal clear 4K video and rapid-fire telemetry from miles away on very limited bandwidth without a single glitch. So wrapping up this explainer, let's hit those key takeaways. We saw how the foundations of AM, varying carrier strength to encode data, are mathematically elegant, even if they are a bit noisy. But its legacy is absolutely locked in. It was the cheap, reliable workhorse that got early RC flight off the ground in the first place. And its future? Well, it didn't just fade away. It evolved. The ghost of AM still lives on right inside the complex digital QAM systems keeping today's most advanced drones connected. I'm going to leave you with one final thought to chew on. We've gone from simple analog pulses twitching a single servo to complex digital QAM streaming 4K video. But as our skies start filling up with completely autonomous UAV swarms, swarms that are going to demand insanely massive, unbroken data pipelines to operate safely, what is the next great leap in radio wave engineering going to look like? Thanks for nerding out and exploring the science of the skies with me,